let's get started. I don't think I projected this slide at the end of last lecture, but just as a reminder, um, if you have completed this, make sure to turn it in. Just put it at the table as you leave. This is for a +5 extra credit. I will post the key today. If you forgot about it and you still want to turn it in, you can turn it by Wednesday, so I won't put the key up. Anybody would like extension? Raise your hand. Wow, okay. So, all right, never mind. Then if you have it, turn it in. If you don't, please by Wednesday. By after lecture on Wednesday, I'll put the key up. Is the key up? Then that means you can no longer turn it in. Okay, this one, I don't know. Do you have this recap slide in your? You do have it. That's good. So I'm not going to go over this. I want to start with chromatography. I just want you to just ask yourself these questions when you're studying so that you kind of capture what went into the lecture. Any questions about previous topics? Because we're going to just switch gears today. Any pressing questions? I take it you understand the material very well, comfortable with it. Great. So we'll move on to chromatography. All right. This topic for me is quite interesting, so I hope I can present it in a way that makes you fall in love with chromatography. Some of you, no matter what I do, you're not going to like it. But I'm hoping for most of you to like this topic because it will come a lot as we progress during the semester, because a lot of the things we're going to cover require chromatography analysis. So I know somewhere along your education you've heard of chromatography, and you probably know what it is. Can anybody, in few words, explain what chromatography is? Brave soul among all the beautiful souls here. Huh? Okay, so the origin of the word has to do with colors because chroma, but
Taking a guess, but I think it's separating solvents by their polarity in some cases.
solutes, yes, separating solutes. Solvents is what you use to separate them. Yes, you're very, very close. And sometimes it's by polarity, sometimes it's by something else. So chromatography is a method of separation. In simple terms, we're separating components that are present in a mixture. And the separation is often for quantification purposes of a particular unknown, or sometimes detection for a presence of an unknown, if it's there or not, like contaminant of concerns. Sometimes it is you want to purify, so you run chromatography to get a component in a concentrated form. So it is basically separation of a mixture of components. So I always tell this story. I've been telling it ever since my daughter was 9 years old. Now my daughter is 15, so I've been telling it for 6 generations. So how does separation happen? So let's talk about an example that's very physical. So there is a store in the mall. It's Justice. I don't know if you know it, but there is a lot of pink and purple items in this store. So my daughter from 9 to 12 was fascinated by that store. So we walk in the store together, right? After 30 seconds, I'm ready to leave. Whereas she goes in and interacts with almost every purple and pink item you can see. So she goes in and she gets lost. So I get separated from her, and I'm ready. I wait at the end, waiting for her to come out. Of course, she doesn't come out. So think about it as a solute or a compound that gets stuck on the column and doesn't want to come out. So what do you do in this case? How do I get it out of the store? What would any parent do at this point? Yell at her? No. What's that? Drag her. Rope and drag. No, something more gentle. What would you do? What? Huh? Huh? Leave her. Yeah, I wish, but no. I buy her something. So get her something that she will interact with and leave the store. So basically, this is what chromatography is about. You get the solute. The first thing, in order to separate, you want to make sure at least one interacts with the phase. Okay, at least one component is interacting. The other one is interacting less or not interacting. So they will leave the column either right away, or they will leave before the other one. In order to get the one that strongly interacted with your material in the column, you change the solvent, you change the mobile phase and put something in there that makes that compound interact with the solvent, so it will just walk out of the column with that solvent. Okay, who can, other than Pam, describe chromatography in 3 minutes? Nobody. It's just me. No, but seriously, it's as simple as this. So you want the interaction to occur first, and then you want the interaction to not occur anymore. So you want the solute to interact, and then you want to drag it out by changing the characteristics of your mobile phase, or the phase that is moving. So definitely I will go over all of the concepts and the different mode of separation, because some separation is based on polarity, like Julianne said, but some separation is based on ionic interactions. Other is based on hydrophobic interactions. So you have different forms of interactions, and we're going to talk about that in very, very much of a detail. Okay, just to know, if you have any idea about what goes on in adsorptive chromatography, which is a form or a mode of separation. Yes, Katie? Yes. So Katie knows that a lot of different interactions can occur. It can either be electrostatic forces like ionic interaction. We call that ion exchange chromatography. Or it can be a hydrogen bonding and hydrophobic interaction. It could be. So this could be by polarity, differences in polarity, or it could be a combination of all. So there are different forms of adsorptive chromatography. We'll talk about that. In reverse phase chromatography, ketone? Okay. A. That A is true. So the mobile phase starts as polar, but then you can change the polarity of the mobile phase. So because you start with mostly water, so the polar compounds would want to go with water. They don't want to interact with the stationary phase that is usually non-polar or less polar. We'll talk again about reverse phase in much more detail, but these are just to see what do you know and where we're at. Let's give some historical perspective. So it all started with David Day, an American geologist, who separated petroleum using fuller earth. So that's the first form of chromatography historically. But he didn't characterize the phenomenon, and he didn't name it chromatography. So the principles of the discovery was given to Svett, who the first one that used packed column actually with chalk and ran leaf pigments through, and they separated into different colors. And that's why he gave it the name chromatography, from chromophore, or compounds that have color. But nowadays, of course, we don't only separate those that are chromophores. We separate all types of compounds. But still, the name came as chromatography because of that discovery. He got the credit for its discovery because he characterized the process much better, much clearly than David Day. And then in the 40s, chromatography that was first discovered and used, or not just discovered, used mostly, is partition chromatography and paper chromatography. And we're going to talk about what is partition chromatography. And of course, you have encountered paper chromatography, yes? You've seen paper chromatography in organic chemistry? Yeah? Yeah. In the 60s, gas chromatography became a hit, and it became an advanced analytical tool, and the equipment were more advanced. So they discovered not just the use of the column, but also a lot of detectors, high-end detectors, and the system became more elaborate. And the growth of gas chromatography was because of the petroleum industry. Followed also in the late 60s, liquid chromatography became more and more known and used, and then followed by supercritical fluid chromatography. We'll talk about that also as well. So this is just to give you a little bit of the history of chromatography. Uses. Where do we use it in food analysis? Can you think of examples? We're going to talk about it all throughout the semester almost, but can you think of examples where chromatography is an analytical tool for food analysis? Mallory?
Maybe to separate and quantify micronutrients?
Macro or micro?
Micro.
Micro, like vitamins, yep. What else?
To identify like aroma compounds.
Flavor compounds, definitely. Gas chromatography is a big one. C- Contaminants, yes, you can determine mycotoxins, for example, using chromatography. You're going to do what? Caffeine. Next week, we're going to do, some of you will do the HPLC lab, where we're going to do quantification of caffeine in different beverages. Fatty acid determination for fatty acid composition. So you'll be doing that also next week in the GC lab, some of you, and then we'll swap the following week. A lot of different components, carbohydrate, amino acids. You name it, we do it by chromatography. So we'll be covering examples of chromatography throughout the semester in different chapters. Okay? It all started with the concept of extraction. Okay, so I'm going to start. Some of you, all of these concepts are new, so please interrupt me if you have questions. I might forget to stop and say, do you have questions? Just please do interrupt. Okay, so it started off with the concept of extraction, where you have a sample, and let's say you want to extract a specific component, like either flavors, for example, or mycotoxins, or any certain component that you want to extract and then further analyze. So oftentimes the extraction is used like you have two liquid immiscible phases, and then that component that you're interested in will be more soluble or liking of a particular solvent than the other. So you are extracting a component using a solvent that the component likes or like to interact with. So extraction can be used as actual means of analysis. Can you think of an example where extraction is the means of analysis? Right?
Like the presence of a toxin.
But there is an analytical method that would be basically an extraction method. Lauren? Okay, you can extract water with the Carl Fisher. That's a good example. Yes. Another one that I was thinking of, you will talk about, we will cover Carl Fisher method in coming lectures. And the one that I was thinking about is extraction of fat. If you want to determine fat content, oftentimes you use solvent to extract the fat and then dry the solvent and then weigh the fat. Then you'll get the fat amount, and that is your method of analysis to determine fat. Preliminary sample cleanup. Oftentimes you need to remove interfering substances. So if you want to determine, let's say, total soluble sugars in a sample, before you do that, you have to extract the fat if you have high fat content. So the first step of cleaning, if it's not drying, is removing fat. So you do hexane extraction, for example, or any other organic solvent extraction to remove the fat and have the material that you will use for determining carbohydrate, for example. Concentration of the component of interest. Somebody said aroma or flavors. So they are present in a very small concentration. In order for you to use an analytical method to detect them, you have to extract them first from the complex matrix. So you extract flavors and then you analyze the flavors, usually using GC. So these are the common uses of extraction nowadays. But like I said, it was the basis for the discovery of partition chromatography, and I'll talk about that in a minute. So the types of batch extraction, you can either have a separatory funnel, which I'm sure some of you, if not all of you, seen that. You do see that in organic chemistry lab, don't you? Those of you that are on track B might not have taken organic chem lab, right? Do you see it in any other labs? In the first chemistry labs? No? Anyway, this separatory funnel, the concept of it is you use an organic solvent immiscible with water, and then you separate components that would be most likely extracted in the organic phase. And then it's a simple separation. Once you shake, 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 and let it settle, and then you would dispense the aqueous that you don't care for, and then collect the organic phase. Continuous extraction, this is the Soxhlet setup, and that's what you will do in the fat lab, where it's a continuous, or in this, well, it is a semi-continuous really, but what happens is you have the solvent, you have a hot plate here, and you have your sample in an upper component, you have a condenser. So once the solvent is heated, it will evaporate, reaches the top, cold water is running, it condenses over the sample, solubilize, in this case it would be your fat, and then get siphoned back into here. You will, at the end of the extraction, it's continuous because it continuously goes up and down, and more pure solvent gets evaporated, gets into your sample, extract more fat, and goes down. So what happens at the end, you'll have your fat and the solvent here, and you have a defatted sample up here. So the countercurrent extraction is the basis for partition chromatography, where you have two liquids that you are using in multiple tubes to separate two different components or more. So I will show you the demonstration in a bit. But what happens here, you have a component or a coefficient that is called partition coefficient, and it is constant at equilibrium. So when you shake the two solvents, then the solute, or the compound that is soluble, will reach an equilibrium. That means it will have a constant concentration in one solvent, in the solvent A, and another constant concentration in solvent B. Depending on what solvent it likes more, it will have higher concentration in that solvent. So in partition chromatography, a series of equilibrium happens so that you end up separating the two from each other. So the partition coefficient is the concentration of solute in phase 1, let's say liquid 1, and then the concentration of solute in liquid too. After you shook it and let it settle, reach equilibrium, then you will be able to get the partition coefficient. If solute A is more soluble in phase 2 than in phase 1, it will have a lower partition coefficient than solute B. Yes, Mallory.
I just realized I don't know if your microphone is on.
This is not a microphone. This is for recording. So it does not project. It just for the... Not here. In lab I do. Does anybody have a problem hearing me? If there is a problem, I can bring an actual mic next time. I thought I'm a very loud person. I do project. But if anybody in the back, can you hear me well? Okay. Thank you, Melanie. I lost my train of thoughts. What did I say last?
You were talking about solute A and B.
Okay, so it's I remembered without you telling me. Okay, so the coefficient, if it is lower for solute A than solute B, that means solute A doesn't like phase 1, likes phase 2. Okay. So what does that mean to you? The countercurrent extraction is basically a series of tubes. That's how it started. A series of tubes where an equilibrium occurs in each tube. So I'm just going to click on this link to show you what I mean by that. Okay, let me get this. Okay, so let's say this is your phase 1, water, and then you add an organic solvent and you have a component, 2 components in there. You shake, and then they're going to take that solvent to the next tube. So this becomes your stationary, water becomes your stationary phase or phase 1, that you have water in each tube. Let's say you have 20 tubes in series. You'll have water in each tube, and then the solvent, the organic solvent, is migrating from one tube to another. When it reaches each tube, it's going to shake and reach an equilibrium. Once it settles, it will go to the next tube, carrying with it the most soluble component. So the most soluble component with the second phase is going to move faster and get to the end faster. And the one that likes the water more is going to be delayed. It will eventually come out, but it would be delayed. So at the end of 20 tubes or 15 tubes or 25 tubes, you will end up separating these components. But in order to determine you want 15 or 20 or 25 tubes, it depends on how different component A is from component B. The closer they are, you need more tubes to separate them. The closer they are in their coefficient of partition coefficient. The further apart they are in their partition coefficient, you need less number of tubes. But imagine this is just a tedious manner of separating. You might need 10 tubes, you might need 30 tubes, you might need 40 tubes. So it's not really a practical mean of separation.
Do you have an example of what compound A and B might be?
Oh, we'll have lots of examples when we talk about all the different compounds that we will separate. Yeah, we'll talk about a lot of examples next week in lab, so don't worry, examples are going to come. I'm just covering concept right now. Okay, so here if you see component A has a 0.5 partition coefficient and component B had a 3.5 coefficient, partition coefficient. So, huh? No. There will be different combinations of solvents that you can use. And just for the sake of simplifying it, I said water and organic phase at this time. Okay, so 0.5 versus 3.5. That means B is going to go with the organic solvent faster, And then the A is going to be retained. It likes the water better. Or vice versa. Did we say that the water is the phase 1? Okay, vice versa. So A will move with the solvent, B will be retained more because it likes the water more. Okay? So previously I had a demonstration. If I hit start, you will visually see how the two are separating, but for some reason now it doesn't work. It requires a certain program that is old and disabled now from these computers. But it's basically it just shows physically how these two will separate as it goes from one tube to the other. But that's the basis of partition chromatography, where you have now, rather than using tubes, you use a column and you pack it with a solid matter, and that solid matter is coated with your phase 1, which is the liquid phase. You coat that inert surface in a column, and then another liquid goes through the column, and that's how the solute or the compound separate between the liquid that is moving and the liquid that is fixed on an inert surface in a column. Okay. Did you die? Well, it got stuck. Let's go back. Now? Okay. So some terms that you're going to hear, I would like you to learn if you don't know them. Solute is the compound that gets solubilized either in an organic phase or an aqueous phase. So when you hear the term solute, you need to think about the compounds we are separating, and it's soluble in different phases. Stationary phase is the phase that doesn't move. Okay? So in these tubes that I showed you, the water was the stationary phase. There's water in every tube, so it's not moving. What's moving from one tube to another is the organic phase, was moving from one tube to the other. So that would be your mobile phase. In a column chromatography, your stationary phase will be packed inside a column, and I'll bring some columns later when we talk about HPLC. I'll show you columns. So your stationary phase will be packed in a longitudinal column, and then the mobile phase would be the solvent that runs through the column. So mobile, it's running through. Okay, so you have a stationary phase and you have a mobile phase. So the stationary phase could be liquid or solid. If it's liquid, then the column will be packed in an inert material, with an inert material. That means a material that does not react with your constituents, and it will have a coating of a liquid component. Or your stationary phase could be solid, so it would be particles that you pack in the column, and these particles are made up of a material that will interact with your different components that you're trying to separate. Then the mobile phase, we call it the eluting solvent. Eluting solvent, the word eluting is to help come out. Okay? Whatever is eluting is the component that is coming out. So it could be an eluting solvent or a carrier gas. In gas chromatography, your eluting or your mobile phase is gas. It's not liquid. So we call it carrier gas. Or it could be a supercritical fluid like CO2, for example, at elevated temperature and pressure. And we'll talk about that when we get to that part. Series of equilibrium or equilibration. So I will later on talk about something called theoretical numbers. So in the column, like each tube that you've seen is, we call it a separate equilibration unit. So in each tube, you have an equilibration going on. In a column, you don't have tubes, obviously. You have theoretical plates. So keep that in mind. You can write it down. Later on, we'll talk about theoretical plate and how equilibrium happens in each theoretical plate. So within a column, there is a series of equilibrium that happens. That equilibrium, that means the amount of time, the amount of solute that is on the stationary phase versus the amount of solute in the solvent. So at some point, you have that constant. Okay, eluent, you'll hear me say eluent, that is a noun. The eluent is the compound that is leaving the column. That is called an eluent. And elute, the verb, eluting. I'm eluting with methanol. I'm eluting with what? Acetonitrile. So elute is the verb we use to when we're saying something is leaving the column, is eluting. And a chromatographic peak, in a chromatogram, we deal with chromatographic peak. So to illustrate, many of you have probably seen chromatographic peak, but let's say our detector is a UV detector, or we have thermal conductivity detector, that's for a GC, UV is for HPLC. But here you will have either absorbance or conductivity, depending on what detector you have attached at the end of the system. So when your compound is leaving, it's getting detected by a detector. The detector could be a UV vis detector for HPLC or conductivity detector for GC, but obviously we have all sorts of different detectors, which we'll talk about for each HPLC and GC. But just to illustrate what I mean, and here you have time. So you will end up having a chromatogram that has time on the x-axis and the detection, either absorption or conductivity in this case. So at every time point, there will be a reading. As time goes by, the detector is going to read. When you start seeing a compound leaving the column, you will start measuring, automatically the system will start measuring absorbance, let's say. So we will start getting absorbance reading, and you reach a peak, maximum absorbance, and then as it leaves the column, the absorbance values decrease, and then until nothing else comes out. So that is your chromatographic peak. It's based on your absorbance or conductivity or whatever you are measuring versus time. So you get a peak. So usually you don't see dots, you see a connected line. So if we have a column where your sample is loaded on the column, let's say the pigments that Svet separated. So they start as a singular band, and as you add solvent, you start seeing them separating, and the separation becomes greater. And as one sample or one component leaves the column, you get that reading. As this one is leaving the column at different time points, you get reading until all of it left the column and you don't see any more reading. Is this clear?
So would the peak be the point when most of it is leaving it at the greatest rate?
Or at the most concentration. So of course here you will have the most concentration in the center of the peak, because we're going to talk about diffusion within the column and longitudinal diffusion, how the component moves. We'll talk about that at the last lecture in chromatography. So the middle is when you have the highest concentration. So the highest concentration will have the highest absorption. Okay? Yeah?
Are you going to do anything that has like multiple HPLC peaks?
Yes, definitely. We'll do that in the LCMS lab. So we'll see multiple components coming out at different time points. We'll talk about separation and resolution of the peaks so that you understand how that happens as well. Okay. Any other questions? These are all good questions. Yes, Lynn?
So for calculating partition composition, we always assume stationary phase to peak phase 1 and the mobile phase to peak phase 2.
Yeah, for simplicity, yes.
Do you choose your solvent then based on what you're trying to?
Yes. So you choose your solvent first based on what stationary phase you have. So let's give you a simple example, which I'll talk about more detail later. Let's say you have a carbonyl group on the stationary phase. That means, let's say C18. C18 is a large carbonyl group. Hydrocarbons, I mean, a chain of hydrocarbon. The longer the chain of the hydrocarbon, the more polar or the less polar is that compound. Hydrocarbons, a long chain of hydrocarbon, is it polar or nonpolar? Nonpolar. So let's say your column has long chain of hydrocarbons. So your column is going to attract nonpolar components, right? So you start with your nonpolar components and you put water as your mobile phase. Why you do that? Because number one, you want your compounds to interact with the column. If they do not interact with the column, there's not going to be a separation. They're going to leave with your mobile phase. So you defy the purpose. So if you have a hydrocarbon group, that means your solvent would be mostly aqueous. Your beginning will be mostly aqueous. So you will have a water solvent. Okay? And then once everything interacted with the column, you change the concentration of your mobile phase and you add some organic in there, organic solvent. Then your compounds are going to start moving and leaving the column. Okay? We'll talk more about that when we cover strengths of the mobile phase and what it means when we say strength of the mobile phase. But definitely, depending on your stationary phase that you're using, you will start off with different combination of mobile phases. So they will be different based on what you have. Okay. We already said it's a separation technique, and it's based on partitioning or distribution. If you hear the word partitioning, that means both stationary phase and mobile phase are liquid, both of them. Distribution, your stationary phase could be solid. So it's distributing between a solid stationary phase and your moving or mobile phase. And often your partition coefficient or distribution coefficient is the concentration of solute in your stationary phase, which is phase 1, phase A, whatever you want to call it. But it's always stationary phase over concentration of solute in mobile phase. And that is at equilibrium. Okay. So there are different types of chromatography. So there are types and there are mode of separation. They're different. So you want to know, when I ask you what type of chromatography you need, you have to tell me gas chromatography, liquid chromatography, or supercritical fluid chromatography. When I ask you what's the mode of separation, you would tell me reverse phase chromatography, ion exchange chromatography. We'll talk about that later. So there is type of chromatography and mode of separation. So you have three different types of chromatography: the gas chromatography, supercritical fluid chromatography, and liquid chromatography. Under liquid chromatography, you have paper chromatography, thin layer chromatography, and column chromatography. So the column, you're actually using a packed column, whereas paper chromatography, you're separating component using a cellulose paper, for example. Thin layer chromatography, you'll be separating using silica spread on an inert material, like glass or aluminum. Yeah.
So those three aren't considered types?
Yes, they are still
Oh, they are
types.
still, okay.
Yeah, they are still types. So liquid, under liquid, you have three different types as well, or subtypes. So the mobile phase and the stationary phase. So in gas chromatography, your mobile phase is always gas. You have always a carrier gas. And usually the carrier gas is an inert gas that does not interact with your column. And then liquid is mostly in gas chromatography nowadays, mostly your column is packed with an inert material and has a liquid coating. There used to be just the solid material with no liquid coating, and it used to be here solid stationary phase. But nowadays applications is mostly where you have an inert solid and a liquid stationary phase in gas chromatography. Paper chromatography is liquid-liquid. In paper, your cellulose is usually immersed, cellulose paper is usually immersed in water, and the water coats the cellulose. The water becomes your stationary phase. And then a mobile phase would be your organic phase, and we'll talk about that. Same with thin layer chromatography. Your silica is not interacting with your compounds. You have a layer of a solvent on the silica, and that would be liquid-liquid. So liquid mobile, liquid stationary phase. Column chromatography can either be liquid-liquid, that's partition chromatography specifically, or this is partition. When you have liquid-liquid, that's called partition chromatography. And then the column could be packed with a solid matter that interacts with your components, so it would be a liquid mobile phase and a solid stationary phase. Okay, so modes of separation. We're going to talk about planar. Planar means paper or thin layer chromatography, but most of the applications nowadays in food analysis is column chromatography. So there are a lot of examples will be given on column chromatography. And then the mode of separation would be, you have 3 modes of separation, and under adsorptive you have further modes of separation. You have size exclusion chromatography, where your separation is based only on size, on molecular size. And you can also hear gel permeation is also size exclusion. So if you hear gel permeation or gel filtration, this is also means size exclusion. So it has multiple names, but they mean the same thing. So size exclusion or gel filtration or gel permeation, they all mean the same thing, separation based on size. Okay? We already talked about partition chromatography, where one compounds will be soluble in one liquid more than the other. Adsorption chromatography, you have multiple modes of separation. You have the reversed phase and the normal phase. Reverse phase is mostly used to separate nonpolar or relatively nonpolar compounds. We'll talk more about that in detail later. And normal phase is mostly used to separate polar compounds. So in reverse phase chromatography, your stationary phase is relatively nonpolar. In normal phase chromatography, your stationary phase is mostly polar. And again, we'll talk more about that later. There's hydrophobic interaction chromatography, which is mostly used in the protein world, separation of proteins or purification of proteins. Affinity chromatography, which is based on a very specific interaction, like antibodies with an antigen or enzyme with an enzyme inhibitor. So this is a very specific interaction, and we'll talk about it more. And the ion exchange chromatography, which is based on ionic interactions, where charge is involved. So all of these, 1, 2, 3, 4, 5, under adsorption chromatography. They're all different forms of adsorption, adsorbing onto the stationary phase. They adsorb via different mechanisms. They either adsorb via electrostatic interaction, ionic interaction, or they adsorb based on polarity and their liking or disliking of polar substances, or very specific interactions as in affinity, or a very hydrophobic interactions as in hydrophobic interaction chromatography. So it's all adsorptive, absorbing onto a surface. This is a very good summary for studying the different methods of chromatography. The mobile, what is mobile, what is stationary, gas and liquid. Your mobile phase is supercritical, and then this is solid. So it's a good summary. And then the retention is based on, we'll talk, gas chromatography, we'll have 2 lectures on that, talk about the types of interaction, but usually it is based on molecular size and polarity. And another one, which is not on that table for gas chromatography, it's based on its boiling point. So this is something else that you can add here. So this is, once we cover all of these, this would be a nice summary table to go back and summarize the information you learned in terms of mobile phase, stationary phase, and the retention, meaning, do you know that term, retention? Claire, what is retention? How long it stays in the column. The more it interacts with the column, the longer is the retention time. Okay? So back to the justice example. I have 0 retention time in the store. My daughter has probably 5 hours retention time in the store. So, well, no longer. Now she goes, ooh, she's 15. Okay. Oh, a note. So the newest edition of the book, the chapter is chapter 12. In the older edition, it used to be, I don't remember what it used to be, 27, chapter 27. But like I said earlier, I strongly advise that you have the newest edition because it is edited and it contains new information. Okay, so I'm just going to stop here for now. We'll continue on Wednesday. Okay, a question. So I have not initiated electronic turn-in, so don't worry about it for this first lab. Turn in your hard copy with the grading sheet only. Thank you. Where? Oh, Brad. Yeah.
Is Haley here? That's the only one that.
No, she doesn't come to lecture.
Okay.
She only came twice.
Yep. That's the only one we're missing today.
Last time she said she had a death in the family, and then she didn't come last Friday, and she didn't come today.
Okay. So she's the
Oh,
only one.
I'm recording still.